Alright, so here is the Socratives for rotation part 2. Number 1, the four forces shown all have the same magnitude, F1 equals F2 equals F3 equals F4. Which force produces the greatest torque, about point O, marked by the blue dot?
Alright, number 1, we're trying to find the largest magnitude torque. So torque, force perpendicular times the distance from my axis of rotation. We'll note that all the forces are the same. So what we're really looking for is, are they perpendicular and how far away are they from the axis of rotation? So we'll notice F2 isn't perpendicular at all, so it's zero torque there. F1 is producing torque, F3 is producing torque, F4 is producing torque, but we really want the one with the largest radius, which would be F1. If I had to pick a second, the second strongest torque, F3 produces more overall torque than F4, because F4, only the component that's perpendicular to that lever arm is going to be producing torque.
Correct answer, A. Good job. Number 2, which of the four forces shown here produces a torque about O that is positive?
All right, so we're going to see if it's positive or negative torque. That's our concern. So positive, it's got to be counterclockwise. Negative, it's got to be clockwise. So looking at these, if I hold my pencil on the axis of rotation, I push like on these forces, I'll note that F3 and F1 are causing this to rotate in the clockwise direction, whereas F4 is causing it to rotate in the counterclockwise direction. So if F4 is our positive torque.
Correct answer, F4, yeah. Number 3, a person pushes vertically downward with a force P on a lever of length L that is inclined at an angle theta above the horizontal as shown below. The torque that this person's push produces, about point A, is?
All right, number 3, we're looking to find the torque from that P. Push. All right, so I need to find the perpendicular component of it first, so I will need to resolve it into components. So this angle here, so we have theta, and so the perpendicular component is going to be P cosine of theta. So then my total torque is going to be P cosine theta times how far away it is from my axis of rotation. L will be my torque. If we wanted to go a little bit extra, we could say this is causing a clockwise torque, so that will have a negative sign on it, but they just asked for the magnitude.
Yeah, cosine, we gotta use the cosine there. If the torque on the object is balanced, then it follows that this object...
All right, for number 4, we're looking at, do the torques balance? So when torques balance, that's telling me that this value right here is 0. If the net torque is 0, that means that alpha must be 0. Torques, remember, only tell me about angular acceleration. That's the only bit they tell me about. They don't tell me about the linear acceleration, they don't tell me about the speed, and they don't tell me about the angular speed. The only thing torques tell me about is alpha. So, correct answer is...
Yeah, all that tells us is that angular acceleration is 0, so it cannot be angularly accelerating. Number 5, if the forces on an object balance, then it follows that the object's center of mass...
Okay, number 5 is similar to the last one. The idea is if I have no net force, well then I'm going to have no acceleration. And remember, forces can only tell me about the acceleration. They can't tell me about the speed, they can't tell me about the angular acceleration, and they can't tell me about the angular velocity. The only thing forces can tell me about is the linear acceleration.
Cannot be accelerating. Forces only tell us about acceleration. Number 6, a uniform beam is suspended horizontally as shown below. It is attached to the wall by a small hinge. The force that the hinge exerts on the beam has components...
All right, so we're looking at number 6. So we want to figure out what kind of forces do we need here. So if I hold this stick like this, what kind of forces is my hand applying here? So one way you can do this is you can actually just hold the stick and you'll know, am I pushing down or am I pushing up to make sure it stays there. The other way to do it, and we're going to try this in the video, we'll see how it works. I'm going to put this in slow motion, I'm going to release this point, and we'll notice that if it moves this way, I must be pushing that way. If it moves this way, I must be holding it to there. And so we're going to watch which way this goes, and that means my force is going to be in the opposite direction. Here we go. All right. Let's see how that worked. I don't know. All right. So either way, when you get this, you should see that the force here, you have to push it out because it's trying to be pulled to the wall by that tension. The other way to think about it is if I choose my axis of rotation here, tension's trying to rotate it this way, so the wall must be applying a force down. So if the slow motion thing worked, great. If not, here you go.
Correct answer there, D, yes, down and to the left. It is possible for an object to be in translational equilibrium, the first condition, but not in rotational equilibrium, the second condition. Can an object be in rotational equilibrium, yet not be in translational equilibrium?
All right, for number 7 here, I want you to imagine just taking a meter stick, setting it on the table in front of you. You can do this with a pencil or a ruler too. And the idea is we want to balance the forces, but not the torque. So if I press up and down with equal forces, the forces balance, but if I'm not pressing in the same location, those torques are not going to balance, and my meter stick is going to start to rotate. Or if I apply 2 torques that are equal, so I push on both sides at the same time with the same force, it isn't going to rotate, but it is going to start moving in this direction. Now, one thing to note over here is, yes, the forces balance. So how do I know the acceleration is 0? Well, when I push on them like this whole thing's going to turn, but the center is going to stay where it is. Okay, and so the center isn't going to move, and so that's how I can talk about the acceleration being 0, because the center of mass is not accelerating.
Correct answer, yes and yes. Okay, we saw 2 examples there. Number 8. You are designing a wheel that must have a fixed mass and diameter, but you have its mass distributed at various uniform ways, or in various uniform ways. If the torque you exert on it is also fixed, which of the wheels shown will have the smallest angular acceleration about its axis perpendicular to its center?
All right, so we're looking for the smallest alpha value. That means we're going to want the largest I value. In order to get the largest I value, we're going to want the mass distributed as far away from that axis of rotation as possible. All of these have the same mass and same radius, so it's really about how that mass is distributed. So looking at those pictures, which one has the mass furthest away?
Correct answer, C, yes, all that mass way at the outside edge. A thin uniform bar has a moment of inertia I about its axis perpendicular to it and through its center. If both the mass and the length of the bar is doubled, its moment of inertia about the same axis will be...
All right, so we're going to double the mass, double the length. What does that do to the I? Well, 2 squared times 2, that gives me 8 times the moment of inertia.
Yes, correct, 8I. Number 10, a glider of mass m on a horizontal frictionless track is connected to an object of mass m2 by a massless string. The glider accelerates to the right and the object accelerates downward, and the string rotates the pulley with a moment of inertia I. What is the relationship among T1, the tension in the horizontal part of the string, T2, the tension in the vertical part of the string, and the weight, m2g, of the object?
All right, so thinking back to the forces chapter, when we had something accelerating, it told us which of the 2 forces would be larger. And so over here, I can see that m2g must be greater than T2 because it is accelerating down. Now, in this chapter, we're talking about torques. So one torque has to be greater than the other. And since they both have the same radius, it's really down to which force is bigger. So since the angular acceleration is this way, it means T2 has to be greater than T1 in order to cause that angular acceleration. Now before, we had T1 equal to T2 because we said this had no mass and was frictionless, but now it has mass, so it's going to require some amount of force to get it to rotate. So that means m2g is the biggest, T2 is the second biggest, and T1 is the smallest.
Yeah, correct answer there. C. A lightweight string is wrapped several times around the rim of a small hoop. If the free end of the string is held in place and the hoop is released from rest, the string unwinds, the hoop descends. How does the tension in the string compare with the weight of the hoop?
Similar to the last one here, direction of acceleration tells us which force is bigger, so since it's accelerating downward, mg must be bigger than tension.
Correct, the tension is less than the weight of the hoop because it accelerates downward. Who will win the race, the hoop or the disc? Let's see.
All right, it's race time. So we have the hoop and the disc, and we're gonna race them down this incline. So I gotta get them started up here at the top. Going to put my meter stick just below and release, and we'll see who wins. The disc clearly wins the race. The disc wins because the disc has a lower moment of inertia, meaning it has less energy it needs to put into rotation, and thus more energy into speed. Another way to think about it is that the moment of inertia is smaller, so it's easier to get it rotating, so it's going to have a bigger acceleration than the hoop, which has a larger moment of inertia, and thus is harder to get rotating. So that was number 12.
Yes, the disc wins because of that lower I value. 13. 4 uniform objects having the same mass and diameter are released simultaneously from rest at the same distance above the bottom of a hill and roll down without slipping. The objects are a solid sphere, a solid cylinder, and a hollow cylinder, and a thin-walled hollow cylinder. Which of the following statements are correct? There may be more than one correct answer.
All right, so here we're looking at multiple objects going down an incline. Now, because they all have the same mass and all start at the same height, they all have the same amount of potential energy at the start, which means when they get to the bottom, they're all going to have the same amount of kinetic energy. What's going to be different is how that kinetic energy is distributed. So the ones with the larger I value are going to require more energy to rotate, so they'll have less energy left over for moving, so they'll be moving slower. The ones with the small I values we're going to require less energy to rotate, and so they're going to have more energy left over for moving. So when they get to the bottom, they'll all have the same kinetic energy. It'll just be distributed among rotational energy and translational energy differently, so they'll have different speeds at the bottom.
Yes, they all have the same kinetic energy at the bottom of the hill. 14. 3 objects, all the same mass m and radius r. Each object is rotating about its axis of symmetry. All 3 objects have the same rotational kinetic energy. Which one is rotating fastest?
Okay, so they all have the same kinetic energy, but we want the one with the largest omega value. So in order to have the largest omega value but the same kinetic energy, it's going to have the smallest I value. So looking at my table, I'm going to look at that hoop. I'm going to look at that sphere that's solid, and I'm going to look at that sphere that's hollow, and I'm going to look and see which one has the smallest I value. That would be the solid sphere.
Yes, the solid sphere. Number 15, a spinning figure skater pulls his arms in as he rotates on the ice. As he pulls his arms in, what happens to the angular momentum L and the kinetic energy K?
All right, so we're looking at pulling those arms in. What happens? So there's no net torque, so friction is pretty negligible between the skates and the ice there. And so there's no net torque. That means my momentum is conserved. And as we bring those arms in, our moment of inertia goes down, our angular velocity goes up. And these change proportionally. So if I do 1/2 the angular moment of inertia, I get twice the angular speed so that I still get the same number. And so if I come over here and do that same thing, half the moment of inertia, but double the angular velocity, because it's squared, I end up with double the kinetic energy. And so when they pull those arms in, they actually do work and increase their speed.
Angular momentum is conserved, kinetic energy increases. Correct. And there we have it.